So we're going to walk through the steps for testing a one-way between subjects ANOVA. And so I have actually created a data set with 3 restaurants. They're all 3 Italian restaurants, but what I've done is I have chosen the top 4 most popular foods from the lunch menu at each of the 3 restaurants and recorded their fat grams, the number of fat grams. So these are the top 4 most popular foods and their number of fat grams at an Italian restaurant called Bertucci's, and then Olive Garden and Carrabba's. And we're going to test this at 0.05. We're going to go through all the steps just like we normally would, and through all the calculations. So let's do step 1, which is stating the hypotheses. Okay, as you can see, this step 1 is pretty simple, just like we've had, and I just basically stated the null and alternative, and I went ahead and included the restaurants, basically that fat grams will not significantly differ, and then in the alternative fat grams will significantly differ. And I kind of clarified it's between popular menu items for the restaurants and the alternative, but that would be fine if you didn't put popular menu items. It's just giving a little bit expanded idea of what's going on. So now we've got step 1 done, and we can move to step 2, which is setting the criteria. So we're going to move forward to step 2. So as you can see, I kind of abbreviated our 3 groups, Bertucci's, Olive Garden, and Carrabba's. And we're going to locate our critical boundary for part of step 2. So just to do this, I immediately just start calculating my degrees of freedom for the ANOVA table, so that at least we can have that done and complete. So first, we're going to do degrees of freedom between, and we know that that is k minus 1. So k is the number of groups. We have 3 groups minus 1. So we end up with 3 minus 1, which equals 2. Then we're going to do the degrees of freedom error. So I just put DFE. Now this is capital N minus K. Capital N is the number of observations in the entire study. So we have 4 observations at Bertucci's, 4 observations at Olive Garden, and 4 observations at Carrabba's. So we have a capital N of 12 if you add all those together. And we know that K is 3. Don't use the degrees of freedom of K, use the actual K. So we end up with 9. So our error is 9. Then our degrees of freedom total is capital N minus 1. We just said N is 12. We're going to subtract 1, so it's 11. We can double check our work and make sure we got it right. By adding together the degrees of freedom between and the degrees of freedom error, we should get the total. So we did get 11, so we're good. So now we need to look up our critical value, and we're going to use the F distribution table on page 483, and we're going to use the between groups as the numerator. So think of it this way: the degrees of freedom we use is equivalent to 2 over 9. You see that? Numerator, denominator. So we're going to go to 2 in the second column, and then go down to 9 in the rows, and we're using 0.05, so we're going to see that it's 4.26. So our degrees of freedom equals 2 and 9, and our F critical value equals 4.26. So that is the level of significance that we're going to be testing this one-way ANOVA at. Now we can move to step 3, and usually just the first part of step 3 is me getting my basic statistics to calculate. So for step 3, we're going to use our data set and just start calculating the basic statistics that we're going to need. So right away, I'm just going to immediately get sums of x's for all 3 of my groups. So this is, I'm going to kind of name group 1, group 2, group 3, so that when I'm using notations, I know what I'm dealing with. So sum of x for group 1, when we add up 19 plus 44 plus 23 plus 36, you should get 122. Then sum of x for group 2, when you add up 10 plus 75 plus 36 plus 20, you should get 141. Then for the sum of x for group 3, we're going to add up 4 plus 55 plus 6 plus 20, you should get a sum of x of 85. Okay, so we have those. Now we can immediately get our means, right? Because we have an n for group 1 of 4, and in group 2, group 2 equals 4, and an n in group 3, which equals 4, so we can get our means. Mean for group 1 is 122 divided by 4, is 30.5. The mean for group 2, which is 141 divided by 4, is 35.25. And our mean for group 3 is 85 divided by 4, which is 21.25. Once you calculate that out. So we have our means. Now we need to get our sum of x squareds for each group. So that means we need to square each score individually for each group and add them for each group. So I'm going to kind of spread this out a little bit further. Sum of x squared just for group 1. So that's 19 squared plus 44 squared plus 23 squared plus 36 squared. Should be getting 4,122. Now we're going to do the same sum of x squared, but for group 2. So that's 10 squared plus 75 squared plus 36 squared plus 20 squared. And you should get 7,421. And then again, sum of x squared for group 3, which is 4 squared plus 55 squared plus 6 squared plus 20 squared. And you should be getting 3,477. So now we have everything we need to get sums of squares for each group, plus the sum of xt and the sum of x squared total. So, and I'm just going to kind of write them down. So I'm going to put here our sums of square for group 1 is 401. So remember, 4,122 minus 122 squared divided by 4 is the sums of squares, just to refresh you. So each group separately. Sums of square for group 2, you should be getting 2,450.75. And then sums of square for group 3, you should be getting 1,670.75. So those are the 3 group sums of squares. We also need 2 other things. We need the sum of x total and the sum of x squared total. So if we take and get the sum of x total, we're looking at 348. And I'm just going to put them next to, because that's basically all of these added up for the total study. The 122 plus 141 plus 85. So now we need the sum of x total squared. So I'm going to put that right here. Sum of x total squared. And I've got 15,020. Now that is basically these added up. The 4,122 plus 7,421 plus 3,477. So now we have everything we need to start calculating our one-way ANOVA. Now we don't have a lot of room, but that's okay. We're going to work with this. So I can kind of show you how this is done. So I'm going to start working on the sums of squares total. Sums of square total. So how we get that is sum of x squared total minus sum of x total in parentheses squared divided by n. So if we get this, we know this first portion is 15,020 minus the sum of x total is 348 squared divided by, remember, we have 4 in each group. We add all those up, we should get 12. If we add up our sums of squared total, or calculate our sums of squared total, you should get 4,928. And now we can just plug that in. 4,928. Bam, we've got our sums of square total. So now we can move on to the next calculations. So I'm going to go ahead and erase this so that I can have some area to work with. And the next thing that I typically work on is the sums of square error. So we'll do sums of square error. And basically this is as simple as the sum of all the sums of squares. So we have the 3 different sums of squares. So it ends up being 401 plus 2,450.75 plus 1670.75. So once you add the sums of square error up, it ends up being 4,522.50. So we can plug that in. 4,522.50. I'm just going to squeeze it in there. Now we have the sums of square error. So we can actually move forward and calculate our sums of square between groups. So again, I'm going to erase this little area so that we can just use that. Bear with me a second. That little space to calculate in. Okay. And to calculate that sums of square between groups, we basically are going to need our sample size and a sums of square means. Okay? So we know our sample size is 4 in each group, and that's really what this is. It's saying we have 4 people in each of the groups. It's a lowercase n. So we know that's going to be a 4. But to get the sums of square means, this is what we need to do. The sum of m squared minus the sum of m total squared divided by k. So we're basically going to do a sums of squares on just the means. So that means we're going to have 30.5 squared plus 35.25 squared plus 21.25 squared. So if you calculate that out, and we're going to do that right now, you should be getting 2,624.375. Now that's just for this first portion, the sum of m squared. But now we need the sum of m. So what we do is we calculate just straightforward 30.5, the means, plus 35.25 plus 21.25. And you should be getting 87. So that goes in the numerator, 87 squared. And we have 3 groups, so 3. So once you calculate that sums of square means out, so 2624.375 minus 87 squared divided by 3, you should get 101.375. Now I just put parentheses around it because that is showing me that this right here is fulfilling this. So we need to plug in our n to multiply that. So our n is 4 right here. So we're going to multiply the 101.375 times 4 to get our sums of square between groups. Because if you stop with the 101.375, that is not the total. You have to make sure you're multiplying by your sample size. So we end up with 405.5. So I can plug that in here, 405.5. Now, we can make sure that we've got our work done right. Just add your sums of square between groups to the sums of square error, and you should get your sums of square total. So the 405.5 plus 4,522.50, you should equal 4,928, or at least very close. Very, very close. It really should come out precise if you're using the right rounding. So now we can start working on our mean squares. So I'm going to kind of do a highlight here. Mean squares is basically, you're dividing across. Going to divide across for each of these to equal. So the first one you divide across is the 405.5 divided by 2. So you should get 202.75. Then we divide the 4,522.50 divided by 9. And you should get 502.50. So now we have everything we need to get our F ratio. Because we're going to, again, I'm going to highlight this. We're going to do basically this as a division to equal this. So 202.75 divided by 502.50. So once you calculate that, you should get 0.404 as your final F, which is not very large. And if you look all the way back at step 2, our criteria was 4.26. So we know we do not have significance. 0.44 or 404 does not fall within that region. So I'll show you here quickly. Here's my little distribution and my criteria again, is 4.26. So 4.26. Anything beyond. And basically, that point 404 falls way over here. Way over. So no significance for that. So because we have no significance, we have no post hoc tests. We do not need to calculate post hoc tests, but we do need to calculate an effect size. So we're going to use our eta squared for an effect size. So again, I'm going to go ahead and I'm going to erase this little bottom area just so I can use this same area and I have to rewrite the tables over again to calculate an effect size. So no post hoc tests, but we do need to calculate an effect size. So to get an effect size, we're going to use eta squared. And so we are going to use the sums of square between groups and divide it by the sums of square total. So it ends up being 405.5 divided by 4,928. Once you calculate that out, you basically should get a number that would be rounded to 0.08. So basically this is suggesting that only a mere 8% of the variance in the fat grams can be accounted for by the different restaurant. Okay, so now we can write our results. No post hoc tests because it was not significant. So we'll go through all the steps and we'll write our results. So let's take note of our eta squared and our obtained f, and we'll write our results in step 3. Or actually step 4, sorry. Here's how your results should look, basically. I mean, not exactly word for word, but it should have basically the same context. You're saying that ANOVA showed there was no significant difference. We have our dependent variable, which is the fat grams, and we have our independent variable conditions, the 3 groups. We have our f and the 2 degrees of freedom in that order, numerator, comma, denominator, for what we look up our critical value. We have our f obtained rounded to 2 decimals. So no matter what, it should be at 2 decimals. We have our p related to alpha, and p is greater than because there's no significance. And we have our eta squared rounded to 2 decimals once again. And that's it. There's no significance, so we don't have anything else to report, and we do not have to say that we don't have to do post hoc tests. It's automatically known. If it's not significant, there is no post hoc test. So there's one way ANOVA in a nutshell. Now, lots of practice is necessary to really get a grasp of this.